Good morning everybody, and a very warm welcome to the NCED today for our Technology Showcase presentation. My name is Rhett Butler. I'm the Chairman of the Research Advisory Committee here at the NCED, and I think what we have is three excellent presentations for you this morning. Each will run for about 20 minutes, and we'll allow plenty of time for questions in between the presentations, and I would certainly encourage each of you to ask each of our presenters anything you might have on your mind at the end of those presentations. But the first presentation today is from the University of New South Wales, and the topic is the reuse of reverse osmosis membranes. In fact, a very topical issue and a project that the NCED is very supportive of. The presenter today is Mr. William Lawler. William is a PhD candidate as part of the project. William is about 2/3 of his way through the project. He's a graduate chemical engineer and also has worked for Sydney Water. And what I would do is hand over to William now to present his project, the reuse of reverse osmosis membranes.
Well, thank you, Rhett, and hello everyone. I'd like to say thank you specifically to the NCEDA for funding this research, and also to all my research partners. Today I'm talking about the reuse of reverse osmosis membranes as an end-of-life extension for used membranes in the desalination industry. Today I'm going to talk about, like I said, the project team and the background, the aim and the methodology, the market for direct membrane reuse and the recycling opportunities, our novel application of converted RO membranes to UF applications. We're going to talk about a number of different alternatives outside of the traditional reuse and recycling framework, and then we're going to talk about one of the tools that we're using as a direct comparison method, life cycle assessment, to determine the environmental feasibility of the different scenarios. We've actually got quite a big team with this project, including the substantial heavyweights at the UNSW, the UNESCO Centre for Membrane Science and Research at UNSW. We've got Michael Duke and Marlene Cran at Victoria University, Brad Ludwig at Monash University. Rhett Butler has been instrumental help in this project from Skyjuice and Siemens. And then we've got various other water utility companies, Sydney Water, SA Water, Water Corporation, and Dow Chemical has also been helping out on the project. Claude. The justification for this project is that the membrane desalination industry has escalated worldwide. As we know, desalination is being used more commonly around the world, and specifically in Australia as well. And of course, now you're probably thinking, what sort of applications can we use this for? Using the test that we've shown, we say that we can use this for potentially for pre-treatment for seawater RO, tertiary wastewater. Some of the more traditional applications for UF flat sheet membranes are a little bit outside the range, including pharmaceutical and food, because of the obvious strict requirements for integrity and hygiene that are required in those industries. But we looked at a little bit more of an outside-the-box application for these reused membranes of decentralized water treatment. Now, this was based off some work done by the EWAG Aquatic Research Institute. They call it a gravity-driven membrane disinfection. It's very similar to the Skyjuice Skybox. Similar concept of providing low-cost, low-maintenance water filtration for decentralized areas. So what we did was we did used a converted module, and as you can see here on the right, we've got this hydraulically driven submerged membrane system with just a simple plate and frame similar to the plate and frame submerged MBR system, but it's purely hydraulically driven, just left to run on its own. We used a variety of different model solutions to determine its performance in fouling and rejection, and it's been working quite well. We've shown that we get over 99% turbidity removal but depending on the membrane that we used and the solution that we were filtering, we got between 60 and 70% organic removal. This graph here, which shows the permeability change over time with some included cleaning cycles. This blue line is where we did not have any cleaning cycles. We just left it to run. You see a little bit of flux stabilization, which is expected in this sort of configuration. But we also tried some basic cleaning methods of just rinsing and wiping down the membrane surface, and we were able to see quite a significant recovery with, incidentally, no change in rejection. We were still seeing solid rejection all the way through this process. So the important thing here is that we were able to develop a cheap system using recycled membranes to produce 20 liters of water per day, and easily scalable. We could just make more plate and frame, make a slightly bigger system for implementation in decentralized systems. So and that brings us to what I call the alternative end-of-life options. We've already discussed the reuse and recycling options, which are traditionally the most effective options for waste management. So we get down into the energy recovery and alternative disposal options. This includes incineration. However, in Australia, waste management traditionally doesn't use incineration. There's no large-scale incineration plants in this country, unlike Europe, where nearly all waste, or at least a large proportion of waste, is used in incineration. And energy recovery and incineration really increases the benefit of that. Unfortunately, we don't do that here, so we have to look at alternative energy recovery options, including a syngas pyrolysis energy generation system, and a novel application that I'm about to talk about is using the polymetric components of the membrane as a coke substitute for electric arc furnace steel making. Now, this is a project that we worked with the Sustainable Materials Research and Technology Center at UNSW. They developed this technology over the last couple of years, and the idea was to use ground-up RM membranes as a feedstock for electric arc furnace steel making. Now, what is an electric arc furnace? Well, there's two types of steel making traditionally. There's the continuous process of a blast furnace and the more batch process of an electric arc furnace. In this picture, you can see the simplified representation of it. Think of it as just a molten steel boiling pot driven by electric electrodes. And as the steel making process requires a coke as a carbon source, they inject metallurgical coke directly into the molten steel. Now, as one of the many reactions that happen in that molten steel, the carbon reacts with the oxygen in the system to produce carbon monoxide and carbon dioxide. That bubbles up through the molten steel. Through subsequent gas release, it forms what they call a foamy slag. Now, the way that it's described to me is that it's a little bit like a cappuccino. You got your foam sitting on top of the molten steel. As you can imagine, that helps retain some heat, increasing the efficiency of the system. It also protects the electrodes and the ceramic walls of the furnace, all in all increasing the effectiveness of the system. So what they're strived for is a more sustainable, consistent foamy slag on top of that molten steel to increase the system. And when you start thinking of it in logical terms, you can see that polymers, well, a high carbon component and with hydrogen, provides a very attractive option as a coke substitute. So that's exactly what's been done. This process has actually already been used in terms of waste tires and plastic bottles in various one-steel plants around Australia, and they've shown really good results with it. So we thought that if it can be used for those sort of high-quality components, we can use it for RM membranes. So what we did was we did bench-scale tests which simulate the injection of the carbon into the system, and then we looked at the foaming performance of the slag. This graph here is just shows you the gas generation and subsequent release in the foamy slag over time. The blue line here is the performance of just a standard metallurgical coke. And you can see the peaks and the troughs are the generation of the gas and the release. and a higher gas generation release was observed with all of the membrane components used. Very similar, in fact, to the rubber ties which are used in the past, however, not as good as the PET water bottles, which was considered the best at this point in time. Now, this sounds like a great idea. Why aren't we all using all sorts of plastic in this sort of way? Well, it turns out in the study that feedstock consistency was vitally important. They don't like any sort of additives in their steelmaking process. The rubber ties provide a very consistent and homogeneous feedstock, which they were able to control quite well. It's easily ground up and has a number of other issues. When high fouling, especially inorganics on the membrane surface, could significantly impact the steelmaking process. We can't use any sort of aggressive cleaning methods because they don't like any oxidative chemicals in their process. So it really detracts from the feasibility of this. So while technically feasible, it's maybe at this point maybe not the best idea. So we've looked at the feasibility of technical feasibility of a number of different options. Now, of course, to make the decision, we've got to look at it in a financial and an environmental point of view. So one of the tools that we're using is life cycle assessment, which looks at the inputs and outputs of all the different unit processes of the option and compares them to a baseline and determines whether it's an improvement or not. So it's an iterative process. It looks at it starts with a goal and a scope definition. You've got to understand exactly what your criteria are and what you're going to be looking at. So in this project, obviously, we're going to be looking at which end-of-life RO option is the best in terms of environmental, human health, and a resource consumption point of view. So we're not just looking at the environmental impact, we're also looking at the human impact, and resource consumption is obviously vitally important as well. So we take one RO membrane, standardized thin film composite polyamide membrane. We generate a model around that. We used life cycle assessment is only as good as the data that you input into the system, into the model. So we've been using primarily first-hand gathered data from our research partners and various industry surveys. The second tier is laboratory-based experimentation for the options that aren't already commercially used. We use our experience and our assessment for that input. We can use a variety of system modeling for things like transport and energy consumption. In this model, we're assuming that the membranes are manufactured in the US, so we use US manufacturing databases for that component. But in Australia, we're assuming that the reuse and recycling is going to be local, so we use Australian databases for that sort of input. Now, what are we actually looking at? Well, obviously, in the green, and this is the diagram of the standard product life cycle. The represented here in the green is the reuse, recycling, and disposal options. You can see that for recycling, you're going back, you're simulating the extraction or the production of raw materials. With reuse, you're reusing the membrane back and substituting out a new membrane, and disposal obviously goes outside of the circular life cycle. So because of that, the reuse system, we actually have to look at and have a detailed model of the production of a new membrane. We need to offset that reuse with the new membrane, which I'm going to show you in a second in more detail. This is what we call the boundary conditions of our model. It looks at all the things that will be considered and excluded for different reasons, and the offsets that we are able to credit to our system. So in the center here, we have our end-of-life membrane. Coming straight off that are the four main categories of reuse options, or reuse, recycle, and disposal options, including, of course, you've got to include transport, which could be different for each option. So, for example, for our reuse option, where you're taking your membrane and using it for a second application, the way that we give it environmental credit is that we're not producing another membrane for that application. You can see that in the slightly darker gray, and you have to consider all the production of all the components and the transport of the new membrane. This similar technique is used for avoided plastic manufacturing for when you recycle, avoided electricity production when you're using some sort of calorific energy recovery, and of course you don't get such a good credit when you're just doing conventional landfill disposal, which leads to the benefits of having a reuse and recycle option. So with that in mind, we then go to the preliminary results from this study. This is an ongoing study. We haven't reached the end of this life cycle assessment at this stage, but we are able to, as it is an iterative process, we are able to do an assessment on the model as we go, so we can see the significance of the different processes and understand how our data is looking and make sure that we have the integrity of the data is at the highest standard. And so from here, we looked at our 4 major options: landfill, material recycling, direct data reuse, and conversion to UF. This is the way that you interpret this sort of data is that you compare it to the option that has the highest impact. In this case, you can see here in the light orange, across all 3 of our broad impact categories, you can see that landfill has the most significant impact, which is exactly what we expect, considering that that's the motivation for the project. Material recycling, interestingly, depending on the way you do it, it can be the most favorable option, which is why it's used for so many different things like PET water bottles and your standard plastics. However, as we discussed earlier, we're only being able to recycle about 40% of our membrane, and with the increased processes of assembly and transportation, we actually don't see that much of a benefit across our categories. However, direct reuse, where we're just looking at a basic characterization and maybe a cleaning step, we see quite a substantial reduction in the impact. And due to the increased chemical requirements and process requirements of the UF conversion, we see that it's still slightly higher. So similar to the direct reuse, but a slightly higher impact. Now, this is the preliminary results, and we will be breaking this down into a number of different categories. We can look at, using the life cycle inventory, we can look at exactly how much of particular components we are consuming, and direct impact on a wide range of criteria. So, and we can compare it to other industries and other options as well. So this is an ongoing model, and it's very interesting. It's a great decision-making tool for when you're deciding on which sort of area to focus on. However, it's a triple bottom line approach, so we've obviously got to look at the financial assessment as well, which is something that we're continuing to look at. But in terms of where we are now and where we're going to be in the next year, we've got ongoing life cycle assessment. We're still looking at different specific applications for our converted membranes as well as our direct reuse membranes. It's obviously very important that we need to understand what they're going to be used for and what sort of market we've got. We're looking at a financial assessment of the options, and we're also going to start looking into other options like a syngas production as an alternative to the more traditional incineration energy recovery options. So that's where we are today. There's lots more to come, but I'd like to thank the NCEDA for funding this research, as well as our wide range of industry and university partners, as they've all been wonderful in their input on this project. So thank you very much.
Thank you very much, Will. I'd like to now invite people if they had any questions that they'd like to address to Will about his presentation. Well, before we start, I can see Tom's looking a bit edgy up the back. He's dying to ask a question. But I've got one for Will, and I think it's something pretty obvious that comes out of this is there's a lot of work that you're doing on a lot of different aspects, and you could go on forever. And you look at the different avenues you're going up. What you've uncovered to date, is there any gut feeling coming out of this as to where you think the best gains are to be made? Is it to look further in terms of this matrix of where some of these recoverables can go, or is it looking at maybe perhaps cleaning and reusing the membranes? Do you have any gut feel as to where you think the best gains are going to be?
Well, I mean, in terms of the existing market, there's already companies that are doing direct reuse. So we're actually in talks with them to understand more about their process at this time. But in terms of an environmental context and in existing what people are actually already doing in the industry globally, it's pretty obvious that direct reuse is one of the most promising options.
So you're saying cleaning the membranes and extending their life?
Yeah. Depending on their application, you may not need a direct cleaning option, but it's obviously an option to do a cleaning step. But yeah, especially considering that we're getting what is considered a pretty good membrane for a lower specified application for 1/3 the cost on average.
Okay, and they've got to go somewhere at the end of the day anyway.
They've still got to go somewhere at the end of the day, so you still got to look at landfill or some sort of disposal option after you're just extending the life cycle, which of course there is still a substantial benefit to that.
Okay, thanks, William. Okay, we've got a question just in the middle here.
Mm-hmm. Thank you.
Especially considering it comes from a PhD student, I wish we could have that at our university more. The reuse component to me is a little bit like extending the life expectancy, so it's better cleaning and so on. But after that, the membrane still will have to find another option after the reuse is lapsed. So if you add an extra 2 years of lifetime, that's good. Is it feasible to still go to UF conversion after that?
It's, in principle, yes, of course, depending on the state of the membrane. But we've shown that even the highly damaged and fouled membranes that we have provided, applied the conversion process to, we've still gotten really good performance from them. So at this point in time, we haven't really seen any sort of membrane state that has like a catastrophic integrity loss when we apply the process to it. So obviously there's more work to be done on the specifics of the different sources, but yes, we could go for that. But when we look at extending the lifetime, in an environmental context, you have to think of every year that you extend the lifetime is another membrane or another membrane year that you don't have to produce. And that's where you get the environmental credit for. So every extension is a benefit environmentally, even if you're using it in a lower specified application.
Maybe just a little add-on. The UF seems to have a huge potential, say, in developing countries in terms of pathogen removal.
Yep.
Can that be filtered in as an environmental effect, like saving people's lives or something?
There is, I mean, the triple bottom line obviously is a social, environmental, and a financial. Social is notoriously hard to categorize. Anyone who's been working and doing that sort of thing, it's really hard to do. So it's worth the discussion, but putting a number to that sort of that sort of criteria is hard, and it's also outside the more direct scope of a life cycle assessment. But it's a great point to bring up. Yeah.
Okay, Olga has a question in front row.
I have a question about the new life. How long you think the second reuse, first reuse could last? And if it's last less than whatever 1/3 of life of new membrane, does it worth it? Because then it's, in terms of cost, it's become practically the same.
Yes, that's a very good point. And we're actually in the process of, we have to get in touch with people who are using second life membranes to understand that. Obviously, it's hard to say. I mean, it depends on what application you're using them for. If you're using a really harsh application, you just buy 3 times as many membranes for the same price, but you don't have to worry about strict cleaning regimens or worrying about sort of biofouling. You can just kind of replace them for a lower cost. So while you may, in the end, pay the same amount of money, you might be getting just a simpler process or a cheaper process in terms of chemical consumption. So the question is quite complex, considering that no one's, well, I mean, there are people doing it, but we need to talk to them. So it's ongoing. Yeah.
Okay, any additional questions? Front row.
Just thinking on the reuse of seawater RO membranes, have you looked at the supply of used membranes versus the demand for second-hand in the UF or other RO applications? My guess is the supply is going to be way more than the demand.
Yeah, and that's, again, why it's so important to look at the existing company that is doing this sort of thing in the States, and we can use that as a model. And that sort of collaboration is ongoing. So there are many questions to be asked about who is using them and what sort of context they're using them in. But obviously, if we're throwing out a lot of membranes, even if they're in good quality, we're going to have to find an application for them. And any sort of harsh, brackish groundwater application has the option to use it, because I know that there's obviously a lot of issue with fouling and membrane damage that can just be avoided by just using a cheap membrane. Yeah.
Was the question more in context of creating a market for UF membrane? Is that what you're thinking about?
Yeah, I think we need to build the market for the second-hand membranes, but just off the top of my head, I'm thinking it's only going to be a small fraction of the total that we're producing. We're probably going to use all the other reuse or recycling options as well, and I just wondered if you'd looked, is that reuse option going to be 20% of the answer, or is it going to be 80% of the answer? I expect it'll be down the lower end. I was interested if you looked at that.
Well, the environmental model at the moment, the way that we've set it up is that it looks at just the life of one membrane. So we just look at, in that sort of situation, if we use that one membrane, how we send it down different paths, what are the impacts? And further down the track, we could look at what percentage is going to different applications and get an overall model. But there's also an effort to set up a system to be able to reuse the Memory Gen project, which is being started up. Yeah.
Over second row in the back.
Thanks. Just a quick question about, you mentioned that the recycled membranes were about 1/3 the cost of a new membrane. I was just wondering, did the cost of the recycled membrane, did that include sort of whatever process you might need to put in place for cleaning, or was it just, is 1/3 just the sort of resale cost, market cost, or did it include all the processes that you'd have to do to get it cleaned? And that would obviously maybe add some more cost.
Yeah, in that survey, there was a number of, some of the membranes had already been cleaned, and that was included in the cost, and they were slightly higher in cost than the average. There was other membranes that were listed as is, but they had a characterization step, so they tested a small fraction of the thousands of membranes from the batch. They had a recommended cleaning regime that where it was able to be followed through, and for an additional cost they were supplying that option. But so there was a variety. Some had been cleaned, some hadn't been cleaned, but there was a detailed characterization for all of the membranes. So,
thanks.
No worries.
Yeah, it seems like at least a healthy proportion of the membranes are eventually going to have to be disposed of. And that disposal option, you looked at one incineration technique that's using an electric arc kind of steel furnace. How about other incineration options? Did you consider any others, or are there any that look like they might hold some promise?
Well, I mean, we looked at them absolutely, and in Europe there is obviously, and even to a smaller extent, United States and other areas around the globe, they do a large amount of incineration. We just don't have that infrastructure here. So in Australia, there just is not a large infrastructure for waste incineration, which is unfortunate because when you add an energy recovery component to waste incineration, you see great benefits, offsets of an electricity generation. So there are a number of companies that we are in contact with who do this pyrolysis waste energy recovery, including syngas, and they are being looked at the moment. So we'll keep you updated.
Okay, any further questions? Okay, well, I'd like to thank Will once again. Thank you.
Thank you.
Thank you, Will.
Thank you very much.
What I'd like to do now is invite everyone for a morning tea break. We're going to have tea or coffee down the corridor on the far left-hand side. We have 2 further presentations after the break. What I'd like to do is ask you to be back here promptly at 20 minutes past 10, so we can keep moving forward, and I look forward to seeing you very soon.